Okay. So in an earlier lesson, we talked about there being a formula for photochemical disassociation, and that we would go into it in the near future, so down the road. So this is that lesson. Technically not a lesson, it's just explaining which one we went to. So Adam's photochemical disassociation formula. Simply put, it's Newton's law of cooling plus speculative formula. Newton's law of cooling, you have TT, capital T, small t equals TS plus parentheses TO minus TS to the natural log E to the power minus KT. So when we're doing photochemical disassociation, percents are heavily used. Get those decimals ready. Okay, so why do we do it? Why was this formula chosen, Newton's law of cooling? Or why is it used? Because used as a loss or separation from process universally alters temperature. So whenever you photochemical disassociate something, there's a change in temperature. Now, we like to instantly think that temperature's a drop, right? But if a temperature rises and it's right here, there's still all of this space. And that's a loss because the temperature's here and now the temperature's here. So there's still a loss from here to here. So that's what we mean by universally. And sometimes the temperature drops as well. So that's why we use Newton's law of cooling, because it's a universal approach. And then of course speculative. So I'm going to give an example, and we're going to be doing where the challenge was put up and somebody solved it. We're just going back through it, etc. So basically what we have here is, for the CO2, we know it's 95%. That's going to be our TO, our initial temp, the overall percent. And we're looking for the oxygen because of, well, the overall photochemical disassociation. The one we're applying it to is oxygen. With that being said, this gets up again and again. The formula is one that just keeps being applied. We're going to isolate it and talk about the oxygen alone. So our overall TO is 95%, which makes it 0.95. Get your decimals ready. On to our need, which is 21%, because we went into that we want the atmosphere super similar. Rubber stamp copy to Earth, so 21%. That is going to be our capital TT, which is our given temp of an object at a given time. And that's the O2. With the remainder, this is important, the remainder is 0.74. You subtract 95 from 21, you get 74.74 as TS, our surrounding temp. Because the surrounding is like, it's kind of like a constant, but it's the surrounding, the remaining, the surrounding. Okay, so plugging that into this formula, our 0.21, which is 21%. 0.21 equals 0.74 plus parentheses 0.95 minus 0.74 E upwards minus KT, constant time, which gives us 0.21 equals 0.95 E minus KT. So now we do a little mathematize it, and we get our natural log number, 0.21 over 0.95 equals ln E minus 88775K. Now, our time is 88775, which is, you know, the solar day of Mars, because we're doing it at Mars. Okay, so then again, we divide it through, we take the K out, boom, 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 isolate the K, and that gives us K equals negative 1 over 88775 log number 0.21 over 0.95. So K equals 1.700202145 e to negative 0.5. That's the answer. Now the cool thing about this for people who've studied this mathematic is its applications, like its natural logarithmic number is an exponential growth. It's in the, like, I'm not going to go too much into math theory right now, but it's in the realm of pi. Like, it's constant, but it's for a natural world. So people that have seen it used know what I'm talking about exponential growth of life, and that this is the perfect fit for it and why that's true. So go ahead and read those if you're not sure what I'm talking about, and there's great instructors out there, and you'll see more what I'm talking about. But that's why we use the natural log number. Okay, now what's interesting about this is that all of these numbers represent, that's the whole 95%, right? So the whole 95% is this. If we were to break it down into individual molecules, say per acres or square miles, it would still be within this range, because this is the entire thing. So if the entire thing, and this is nothing, this is 0, and this is the completeness of it, and that's this value here, there would be different molecules that would fit this. Like if it was 1 acre, it might be a version of this whole number right here. But if it was 10 acres, it might be this one. If it was 100 square miles, it might be this one. But it's all a growth onto this one, and that's the biggest growth for the 95% into 21% with our remainder. So what you're going to ask next is, what are we going to do with that 74% remainder? Which is actually what the lesson we're going to be going into is about. I more just wanted to get this out about what the answer to yesterday's challenge was, and congratulate those who figured it out. But we're going to go ahead and go a little bit further and just show you that how this is used in the entire formula. So we put in an absolute value of angstrom here, right? And so when you do that, you have the absolute values normally this. It is just a deviation of it. And then you get this. And you know absolute values, the nature of it says it. You cannot come out of the brackets unless something happens. That's basically what absolute values do. Absolute values are like this. So let's just say, for example, I had a tragic -4 here, but I saw it was absolute value. Well, when it comes out, it would just be 4. Okay, so we use absolute values, but we put the angstroms in there. So no matter what, this value cannot come out until it's positive, until it's reached an angstrom ability. You won't be able to solve it without that. So if you just think, oh, well, it was a negative, or it was a 1.700202145 natural log to the -5e to the -5, that's it. Okay, you're going to be able to do nothing with it. So that's why we put the absolute value of P, which is 0 angstroms, in an absolute value container. Okay, then we plug in the speculative. And again, this is for the lesson of Mars that we were talking about. Mars atmosphere plus LDD1 over level degree deck 2, 590 watts per meter squared, 88775 times 7, with our LDs D1 of 2, so which is 1 through 30, times the parentheses 1 plus 621,425 divided by 7, because it's a non-stop per circular day, 90 degrees, and we know our capital RRR is using the solar activity, right angles, infinite expanding, and then we're calling on Jupiter's core. And then, you know, our P0 hertz over 25 times 9 for PPF tab across LDD, 1 of 2, all of them with our sine oath would give us our angle. So that's just a demonstration of what we did yesterday, numerically mathematized numbers. Okay, so yeah, so that's actually it. Well, one thing I want you to remember though is that this formula will be used constantly to solve anything. Like I just showed how it was done taking oxygen out of CO2, but where'd the carbon go? So we read 0 with the CO2, right? With the O2 of it, where'd the carbon go? So that's the whole point. You're just going to consistently use this. You're going to consistently use it. Yeah, so let's go ahead and get ready for the next lesson.